I'm excited to talk to you today about unit cells because unit cells are kind of the fundamental piece of a crystal structure. So crystals or crystalline material like ionic compounds are made up of individual repeating box-like units that make up this orderly array that we perceive as crystals. So when you think of a crystal, you think of this kind of cool geometric three-dimensional shape to it. And all of that shape comes from the individual repeating units that make it up at an atomic or ionic level. So the unit cell is kind of the smallest repeating unit, and it can be large. They can be multiple atoms worth, and we can kind of get into this in more detail when we get into real examples of it. But for right now, I just want to talk about kind of the different fundamental types of unit cells, at least the cubic ones, and then we'll get into more complicated detail in future videos. But for now, cubic unit cells are the simplest of the unit cells. And if we think of having an atom on each of the corners of the cube, or an ion at each of the corners of the cube, then that's going to be a simple cubic unit cell. Now, when we're looking at unit cells, we usually will think of the kind of the three-dimensional axes, and if we place this right at this front corner here where this atom is, then we can kind of label everything from there. So in a simple cubic system, here's my A, my B, my C, my A, my B, my C, then they're all equal to each other in terms of length because it's a cube, right? So a cube has equal length times width times height. All of those side lengths are equivalent. And then the angles within them, when we're defining unit cells, the angle between A and C, so A and C, is labeled as beta. So it's the Greek that's the different letter. So that's my angle beta. The angle between B and C here is alpha. Again, kind of the opposite Greek directional kind of term there. And then this angle between A and B, kind of in the plane here, is gamma. Okay, so alpha is between alpha is between C and B, beta is between C and A, gamma is between A and B. So in this case, because it's a cube, alpha is equal to beta is equal to gamma, and all of those are 90-degree angles because it's cubic. Okay, so that doesn't blow you over with the complexity of anything. It's a cube. We kind of all know what a cube looks like. This would just be the simplest thing if all I had were atoms on each of my corners here. Now, the limitations we have of drawing something like this come from the fact that we visualize atoms as a sphere and that we visualize the bond, whether it's an ionic bond or whatever kind of attraction that's between these things, as sort of a stick. So this ball and stick model is a little bit misleading, and even though it's kind of handy and it helps us to visualize what this thing looks like, it limits us because these atoms actually take up space. These ions take up space because of the electron cloud they're in. So if we're actually visualizing this in terms of this atom, say, or this ion on the corner, then realistically it's going to be taking up some space, right? If I kind of fill this in, it's not that it's a ball on the corner. It's actually just a piece of an atom on the corner there, right? And it's actually being shared by all of the other boxes that are near it, right? So if I draw another box here, dun, 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 here's another unit cell next to it, then it's actually being shared by this side as well. So we have right? So it's actually just a part of an atom that is in that one unit cell, right? And then we'd have another one that's going this direction, that is taking up space. It's going to get pretty messy pretty quickly. And then we have this one that's you know, taking up space. Right? So if we're picturing each of these things here in the corners, then these things are all taking up some space. There's sky. But it's not a full atom, right? When we draw it ball and stick, it looks like we have an entire atom and then they're stuck together with sticks. But these things are actually taking up some amount of volume, right? There's electrons on them. The electrons take up some space. We kind of visualize them as spheres, but it's not that there's one sphere that's attached to each of these unit cells. Actually, each of these corners is shared by, if we're kind of drawing these guys in, each of that corner is connected by a bunch of other unit cells, right? So if I was to draw these out repeating in multiple directions, right, in all three-dimensional spatial directions here, then this one atom or this one ion is actually being shared by this unit cell, this unit cell, this one, right? Kind of on that bottom layer, so that's 4. But then it's also shared by this one that's on the top, this one that's on the top here, one that's on the top here, and one that's on the top here. So this one atom or ion is shared by 8 different unit cells. So that means that in any one given unit cell, right, that atom is actually only 1/8 of an atom, right? Which sounds weird because of course we can't talk about 1/8 of an atom, but when we're doing an accounting then, each of those corner atoms is really 1/8 of an atom. So if I was to say how many atoms are in this simple cubic unit cell, then I would say, well, I have 1, 2, 3, 4, 5, 6, 7, 8 atoms, right? And each one of these atoms is really 1/8 of an atom. Then that gives me 1 atom total that is in that unit cell. Now, again, that's kind of weird to think about because I have each of these on the corner. It looks like I have 8 atoms, but each of those atoms is only a part of an atom because it's being shared by the unit cells that are neighboring it. Okay, hope you're hanging in with me so far. All right, there's our simple cubic unit cell or primitive unit cell. The next of our cubic unit cells is called body-centered cubic, and it's sometimes just kind of they use the acronym BCC for it. So body-centered cubic. So we start off with a simple primitive unit cell, and at the center of it is a complete whole atom. So we can kind of think about this as, you know, the sphere at the center of my atom. I'm using 2 different colors just to show the difference between them, but they could be all the same thing. You could have a metal, for example, that just goes into the body-centered cubic crystal structure, so its unit cells look like this, and they're all the same atoms. I'm just, for the purposes of illustration here, making 2 different colors. Okay, so because it's cubic, my A, B, and C are all equal to each other, because it's a cube, and my beta, alpha, and gamma angles are all 90 degrees. And now if I asked how many atoms are in this body-centered cubic unit cell, then we would say, well, we have these ones in the corner. There's 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. And each of those atoms is 1/8 of an atom. So that gives me 1 atom from the corners. And then this atom at the center, at the body center, is not being shared by any other of my unit cells. If I was to draw unit cells in all directions, then there would be an atom or an ion that's at the center of each of those unit cells, but they're not being shared by any others. So it's 1 atom completely surrounded by that box, that cube. So there's 1 times, 1 over 1, if you want to think about it that way, which gives you 1 atom from the body center. And that means total in this structure, I have 2 atoms that are in this unit cell. And again, that looks weird because if you look at it, it looks like there's 9 atoms, right? But we don't have 9 atoms, we have portions of them, fractions of them in this unit cell if we think about this in terms of space filling. But one whole one is at the center, and then we get 1 atom that's accounted for by the 1/8 of the atom that we have at each of the corners. Okay, so it's stretching your geometry brain a little bit. Now the third kind of cubic unit cell is called a face-centered cubic, or FCC. So again, we start off with the cubic unit cell, so we have atoms on each of the corners, and now we're going to put them on the faces. So I like to think about this like a dice. So I have my little ducky dice here. And if we picture that there's an atom that's at the face of each of these kind of surfaces, right? So we're picturing the cube here. Then if I have an atom that's on each of the faces, we can kind of draw it like this. And I try to draw it in alignment with the plane. But again, we're picturing these things in 3 dimensions. So these ones on the faces are going to be shared by the one that is their neighbor. So you kind of picture a dice that has a 1 on each side. Not this kind of one, but like a spot on each side. And these things are kind of opposite each other. Like that. Right? And we have these guys on each of the faces. There's nothing at the center of this. They're at the faces. And if we're visualizing this at the side, then kind of half of this atom is going into this space, and the other half is going into this unit cell. So this one next to it is going to have half of this guy, and this unit cell has the other half. So when we have a face, because we're being shared by 2 unit cells, then this one is really half of an atom. So we have 8 atoms on the corner, and each one of them is 1/8 of an atom. So that gives me the 1 atom from the corners. And now I have 1, 2, 3, 4, 5, 6 faces, and each of the faces is shared by 2 of these unit cells. So that means that I have half of an atom here, half here, half here, half here, half here, half here, and that gives me 3 atoms total. So when I add these guys together, I end up with 4 atoms total in this unit cell. And again, it's kind of tricky because I have 8, and then it looks like I have 14 atoms, but I don't have 14 atoms because each one is a portion of an atom. There's no one atom or ion that is enclosed within this unit cell like we have with the body center. So these ones on the faces are going to be shared by the unit cell that's above and the unit cell that's below, or to the ones to the sides, etc. So it takes some kind of visualization to picture these things propagating out in 3 dimensions and see how that all kind of works out. Okay, so figuring out the number of atoms in a unit cell is important because that kind of gives you information about the structure. Knowing how they're oriented, whether they're on faces, whether they're on the body, whether they're on the edges, that's also a possibility. Those are all going to be interesting pieces that will tell you more about the overall macro structure of these solids. So the way that these things pack together is going to give you information about what they look like from a visual standpoint, which is just kind of cool and wacky. As always, if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.